Section 3.3, Video 1, Compound Interest. In this video, we will cover the following objectives: solve problems involving compound interest, and compute compound interest formulas for principal, rate, and time. As a reminder, simple interest are accounts with a one-time lump sum deposit called principal, and interest is calculated only one time. Compound interest is when the principal amount is invested once. However, unlike simple interest, the interest for the account is calculated on the entire principal at regular intervals throughout the length of the account. The formula for compound interest is developed in the textbook. However, here we have the formula below and the different variables. A stands for the amount in the account, the total amount. P is for the principal, the amount initially deposited. 1 plus R stands for the interest rate, written as a decimal. T is the time in years. M stands for the number of times interest is compounded in 1 year. And N, the exponent, is the number of times interest is compounded over the life of the account. Let's take a look at example 1. Zara deposits $8,200 into a savings account that earns 3.6% annual interest compounded semi-annually. Find the amount in the account at the end of 15 years. At the end, we're also going to find the amount of interest that accumulated or was earned. Let's start out with part A. In part A, let's fill in the information that we know. We know we want to find the amount in the account, so our goal is to find A. We were given that the principal is $8,200, the amount initially invested. We also know the rate of 3.6% that we can write as a decimal, 0.036 or 36 thousandths. The next value they give us is that interest is compounded semi-annually. So semi-annually would mean 2 times a year, so that means our M is equal to 2 times a year. To calculate N, we want the number of times interest is compounded over the life of the account. So to calculate N, we're going to say that interest is calculated semi-annually, which we just said was twice a year, times the number of years. And in part A, that was told to us as 15 years. So if you'd like, a shortcut to variable N is M, the number of times you're going to compound in 1 year, times T, the total number of years. In this case, that's twice a year for 15 years, or a total of 30 times that interest will be calculated. Now let's go ahead and substitute this information into our formula for compound interest. So we know we're finding variable A. Our principal is $8,200. 1 plus our rate as a decimal is 0.036. M we said was 2. And our exponent is going to be 30 because that was 2 times a year for 15 years. Working with order of operations, we're going to simplify inside the parentheses first. So we get 1 plus 0.018 to the 30th power. Again, we're still going to simplify inside the parentheses and add. And we get 8,200, 1.018 to the 30th power. Exponents come before multiplication. So we have 1.018 to the 30th power. And keep as many of these decimals on your calculator as you can. 1.707785571. And then we're going to multiply by 8,200. And I'm going to go ahead and round to 2 decimal places since we're working with money, $14,003.84. So at the end of the 15 years, the account will become worth $14,003.84. Part B then says, find the amount of interest. So to find the interest I like to say is the difference between the money you put into the account and the money that can be taken out. So the money at the end of the account that you can take out is $14,003.84. But the money that was initially put in was $8,200, that initial principal. So subtracting, we find that the interest is $5,803.84. Before beginning example 2, let's take a look at daily compounding compared with ordinary interest. Daily compounding would be every day, and there are 365 days in a year, so that would have an M of 365. However, and that's used in our textbooks. There are some textbooks that use ordinary interest, so if you see something that says ordinary interest, then that's 360 times in a year. Okay. Example 2. Suri is saving money to buy a car in 4 years after graduation. She plans to set aside money into an account earning 6.3% interest compounded daily. She predicts that she will need $8,500 to purchase the car. Part A, find the amount Suri should deposit into the savings account today so that it will grow to become $8,500 in 4 years. So for Part A, we need to find the principal because we know the amount in the account needs to be $8,500. Some other information provided is that the interest rate R is 6.3%, which becomes 0.063 as a decimal. And interest is compounded daily. So if we're looking at daily compounding, that ends up telling us that our M is 365 for 365 days in a year. Then to find our N, the number of times we're going to calculate interest over the entire 4 years, we would take 365 times to calculate interest in 1 year times 4 years, and we get a total of 1,460 times that interest would be calculated. Now let's go ahead and use our amount in the account for compounded interest and fill in what we know. We know the amount needs to become $8,500. We don't know the principal. 1 plus our rate, we decided as a decimal, was 0.063. Our M is 365 days in a year. And then our exponent was 1,460. Again, working with order of operations, we're going to simplify inside the parentheses first. 0.063 divided by 365 is going to be a very small amount. Sometimes it's actually shown as in scientific notation. Writing it out in decimal form, we get 0.000172603. And then when adding the 1.000172603. So just take it one step at a time. Now let's go ahead and calculate the work through the exponent. So our decimal to the power of 1,460 gives us 1.28656806 equals 8,500. And to get our variable p alone, we'll divide by that 1.28656806 to both sides of the equation. Notice that I'm keeping as many decimals as I can until the final stage. And I'm going to take that 8,500 divided by the decimal we just said, 1.28656806, and I get rounded to the nearest penny, so 2 decimal places, $6,606.72 is the principal. That's the amount that needs to be deposited now to accumulate to $8,500 in 4 years' time. Part B, find the amount of interest. The interest is the difference between the money put in the bank and the money that's able to be taken out. So the money, the initial deposit, is our $6,606.72. The money that will be available at the end of the 4 years is $8,500, and we need to find that difference, a subtraction. So when we subtract, we get a total interest of $1,893.28. Example 3. Grayson has $2,500 to deposit into an account. The bank employee tells him it will take 10 years for his money to grow to $4,000. If the interest is compounded monthly, what's the annual interest rate the bank is offering for this account? At the end, we'll round to the nearest hundredth of a percent. Let's start with the information given. The principal is $2,500. The amount it's going to grow to is $4,000. We know that the time is going to be 10 years. We don't know the interest rate, but we do know that interest is compounded monthly. Which tells us our M is 12. And to find our N, we're going to take that interest is compounded monthly times the 10 years for a total of 120 times that interest is compounded during the life of the loan. Substituting in the information that we know into our compounded interest formula, we get that 4,000 equals 2,500 times 1 plus, we don't know the rate, so we'll keep the R variable, over 12 for monthly compounding to the exponent of $120. Since we can't simplify inside the parentheses, we're going to find another way to start, and we can divide away that front multiplier of 2,500. And we find that we get 1.6 equals 1 plus R over 12 to the 120th power. To get into that variable, we're going to have to eliminate that 120th power. So we're going to take the 120th root of 1.6 and the 120th root of 1 plus R over 12 to the 120th power. Keeping as many decimals as I can, the 120th root of 1.6 is 1.003924377. And on the right-hand side, we're left with 1 plus R over 12. And now those parentheses are no longer really needed. We can subtract 1, which gives us 0.003924377 equals R divided by 12. And then to eliminate the 12 and get the R by itself, we'll multiply both sides by 12. And we end up with a rate of 0.04709252. And that tells us if we change that into a percentage, it would be 4.709%. Or if we're rounding, like they said, to the nearest hundredth of a percent, that's going to be 4.71% as the approximate interest rate. Let's take a look at example 4. Ayana wants to know how long it takes her to make $1,200 deposit to increase to $1,500. The annual interest rate is 6% and it's compounded quarterly. How long would it take for her deposit to increase to $1,500? Let's start out with the information given. Our principal is $1,200 and the amount it needs to increase to become is $1,500. The rate is given as 6% or as a decimal 0.06. Since it's compounded quarterly, that's going to give us an M equal to 4 because there are 4 quarters in a year. And then we're going to find our n, our exponent, as 4 quarters in a year times our time. We don't know how many years it's going to take. That's what we need to find out. So we're just going to leave t for time. So our exponent is going to be 4t. Let's go ahead and put this information into our compounded interest formula. So our amount is going to be $1,500, our principal $1,200, and we have 1 plus our rate 0.06 divided by 4 for compounded quarterly, and our exponent is 4t. Again, we can't quite simplify with the exponent, but we can simplify inside of our parentheses. So I'm going to take 1,500 equals 1,200, and 0.06 divided by 4 ends up being 0.015. Adding 1, 1.015 to the 4t exponent. And again, we can't work on the exponent next because we don't have that variable t, but we could divide away the 1,200. So we end up with 1.25 equals 1.015 to the 4t power. And again, whether you keep the parentheses or not, they're really no longer needed at this point. Okay. To solve, we're going to take the natural log of both sides. Natural log of 1.25 equals the natural log of 1.015 to the 4t power. And using our property of logarithms that exponent will become the front multiplier, we can rewrite it as natural log of 1.25 equals 4t times the natural log of 1.015. And we can divide. To get the t alone, we'll need to divide by 4 and the natural log of 1.015. So we end up with the 4's reducing to 1's and the natural log of 1.015 reducing. And we end up with t equal to 3.74688 and a few more decimals. So our t is approximately 3.7 years. And that ends example 4.